Hi class, so today here in Advanced Engineering Mathematics for Civil Engineers, we're now going to discuss our fourth lesson, which is about systems of linear equations. So for this topic, our intended learning outcomes are as follows. So the first one is students must be able to evaluate systems of linear equations using direct elimination methods, namely Cramer's rule, Gauss elimination method, Gauss-Jordan elimination method, matrix inverse method, LU factorization, that is Doolittle's method and Kraut's method, and Cholesky method. And students must be able to evaluate systems of linear equations using iterative methods, namely Jacobi method, Gauss-Seidel elimination method. So matrices can be used as solution to systems of linear equations. So there are two different approaches for solving systems of linear equations. So the first approach is direct elimination methods, and the second one is iterative methods. Okay, so for direct elimination methods, okay, it includes Cramer's rule method, Gaussian elimination method, Gauss-Jordan elimination method, matrix inverse method, LU factorization, which includes Doolittle's method and Kraut's method, and the last one is the Cholesky method. Now, for iterative methods, we have Jacobi method and Gauss-Seidel elimination method. So we are going to discuss all of these methods, okay, in solving for systems of linear equations. Okay, so systems of linear equations expressed as matrix. So we can actually express a system of linear equations into a matrix form or matrix equation. Okay, so let's say we have here this system of linear equations. So these are linear equations. Okay, so this A11, A12, and so on, and up to A33. So these are the coefficients of the variables here in this linear equations, no? And x, y, and z, those are the variables, okay, for these linear equations. And this b1, b2, b3, they are the constants, okay? So from here, this system of linear equations, we can rewrite this as a matrix equation, or we can express this in matrix form. So this will be the matrix form of this system of linear equations. Okay, so this will be the coefficients, no? So this will form a 3 by 3 matrix. Okay, so since this is a 3 equation, so the coefficients, okay, of this system of linear equations, it will form a 3 by 3 matrix. Okay, and also it will be multiplied by the by a column, okay, wherein the elements here are the variables of the linear equations. Okay, so the variables here are x, y, and z, and this will be equal to the constant. Okay, and if you're going to perform actually the operation for this, so this is actually multiplication of this 3 by 3 and this column matrix. Okay, if we multiply this, okay, and apply the concept for equality, so it will just be A11 times x plus A12 times y times plus rather A13 times z is equal to B1. And that is actually the equation 1, right? And if we do the same to this second row and third row, we multiply it in this column, okay, and equate it in this to this constants, no? So it will give you the second and third equation here. So this is really equivalent, okay, to this system of linear equations. So this is the matrix form or matrix equation of this system of linear equations. So also we have here what you so-called coefficient matrix. So the elements of the matrix, okay, of the coefficient matrix, okay, are called, so let me repeat that. The elements of the matrix, this matrix, no, are called coefficients of the system of linear equations, and the matrix itself is called coefficient matrix. So the matrix wherein the elements are the coefficient, okay, of the variables in our system of linear equations are actually called coefficient matrix. Okay. So also we have here what you so-called augmented matrix. So the matrix, okay, as you can see here, so obtained by adjoining the respective components or constants of the system of linear equations to the elements of the coefficient matrix as an n plus 1 first n plus 1 first column is known as the augmented matrix of the system. So augmented matrix, so we just have to put the constants, okay, besides the coefficient matrix, no? So this will be the um, augmented matrix. Let us now discuss the first direct elimination method. Okay, this is called Cramer's rule method. So consider the system. So this is a system of linear equations. We have here three equations. Okay, so let A be the coefficient matrix of the system. So after that, okay, so to determine the values of x, y, and z, the Cramer's formula is, okay, so in order to solve for the system of linear equations as seen in the previous slide, okay, we just have to solve for the values of x, y, and z. Okay, and for the value of x, okay, using Cramer's formula, it will be the determinant of n of x over determinant of matrix A, that is the coefficient matrix A. And to solve for y, that is just determinant of n of y over determinant of a, and z is equal to determinant of n of z over determinant of a. Okay, so we are going to determine how to solve for the n of x, n of y, and n of z in our succeeding slide. Okay. So to determine determinant of n of x, determinant of n of y, and determinant of n of z, we just have to replace the coefficients of x, y, and z respectively by the constants of the system. Okay, so let's say for determinant of n of x, this n of x will be the matrix form, okay, by replacing, okay, the column, okay, wherein the x variables are located, okay, we will replace that with the constants. Since this is n of x, okay, we will replace the column, okay, wherein x are located, okay, with constants b1, b2, and b3. So this will be the n of x, and solving for its determinant will be the determinant of n of x. Now for the n of y, so this matrix, it will just be formed by replacing, okay, the column, okay, of the where the y variables are located, which is the second column. We will just replace that with the constants, no, constants b1, b2, and b3. So this will now be the n of y, and solving for its determinant will be the determinant of n of y. Now for the n of z, so n of z will be formed, that matrix will be formed by replacing the column wherein the z variables are located with the constants b1, b2, and b3. And solving for its determinant, that will be the determinant of n of z. So let's start solving problems using Cramer's rule method. So for the first problem here, our system of linear equations here are 3x plus y is equal to 2, and then 2x plus 3y is equal to -1. Now for number 2, this is 3x plus 2y plus z is equal to 8, 2x plus y plus 3z is equal to 7, and then 5x minus 3y plus 4z is equal to 3. So let's start solving number 1. Okay, so to solve for this system of linear equations, we just have to solve for the value of x and y. Okay, so for using Cramer's rule method, the coefficient matrix of this system of linear equations, so the coefficients are 3, 1, and then 2, and then 3. So that will be our coefficient matrix A. Now to solve for x, our formula for x and y, our formula for x is determinant of n of x over determinant of A. And then for y, that will be equal to determinant of n of y over determinant of A. So for A, the coefficient matrix A, okay, we just have to solve for the determinant of this coefficient matrix A. And for determinant of n of x, determinant of n of y, we will determine that. Okay, so for determinant of coefficient matrix A, it will just be the determinant of this 2 by 2 matrix. So solving this will just be 3 times 3 minus 2 times 1. That will be 7. Okay, so that will now be the determinant of A. Now for the n of x, so to obtain n of x, we just have to replace, okay, the column wherein the x variable is located. Okay, we will just replace that with the constant. So the constants here are 2 and -1. So we will replace, okay, the first column with constants 2 and -1. And solving for this determinant, okay, so this will just be 2 times 3 minus -1 times 1. So that will be 7. So that will be the determinant of n of x. Now for the determinant of n of y, okay, so we just have to replace here, okay, from our coefficient matrix, we just have to replace the column wherein the y variable is located. So our the column wherein y variable is located is here in the second column. So we will replace this second column with the values of the constants, which are 2 and -1. So solving for its determinant, okay, this will just be 3 times -1 minus 2 times 2, no? So that will be -7. So this will now be the determinant of n of y. So solving for x, we already have determinant of n of x, which is equal to 7. And the determinant of a is also 7. So 7 over 7 will just be equal to 1. So this will now be the value of x. Now for the value of y, our determinant of n of y is -7, and the determinant of a is 7. So this will be equal to -1. So this will be the value of y. So these are the answers for number 1 using Cramer's rule. So x equal to 1, y is equal to -1. Now to solve for the second example, okay, so to solve this system of linear equations, we just have to solve for x, y, and z using Cramer's rule. So using Cramer's rule for the coefficient matrix A, okay, so we just have to form the coefficient matrix from the coefficients of the variable of the linear equation. So that will be 3, 2, 1 for the first row, and then 2, 1, 3 for the second row, and then 5, -3, 4 for the third row. Okay, so using Cramer's rule, again, the formula for x, y, and z. For x, that is just determinant of n of x over determinant of a. For y, that is determinant of n of y over determinant of a. And for z, that is just determinant of n of z over determinant of a. So let's start solving this. Okay, so for determinant of A, we just have to solve for the determinant of coefficient matrix A. So this is our coefficient matrix A. So solving this using basket method, so we can use basket method since this is a 3 by 3 matrix. So it will give you 42. So you can solve this using basket method, no? Okay, so that will be the determinant of A. Now for the determinant of n of x, so your n of x, again, it will be, that matrix will be obtained by replacing the column wherein the x variable is located, which is in the first column. So we will just replace that column with the constants 8, 7, and 3. So solving for its determinant, it will give you 42 as well. So this will be the determinant of n of x. So you have to solve this using basket method to solve for this determinant, and it will give you 42. Now for the determinant of n of y, for n of y, okay, so this is obtained by replacing the column wherein y variable is located with the constants, okay, or by the constants. So the constants are 8, 7, 3. So this will now be the n of y, solving for its determinant using basket method. So it will give you 84. So that will be the determinant of n of y. Now for the determinant of n of z, okay, so for the determinant of n of z, for n of z, so we just have to replace the column wherein the z variable is located. We just have to replace that by the constants 8, 7, and 3. So solving for the determinant of this n of z, that will give you the determinant of n of z, and that will be 42. No? So using basket method to solve that. Okay, so from here, okay, we can now solve for x. So the determinant of n of x is 42 over determinant of a, which is also 42. So that will be 42 over 42, and that will be equal to 1. So that will be the value of x. Now for the value of y, the determinant of n of y is 84, and the determinant of a is 42. So 84 over 42 is 2. So that will be the value of y. Now for the value of z, so determinant of n of z is 42, and the determinant of a is 42. So 42 over 42 is 1. So that will be the value of z. So this will now be the answers for second example, no, using Cramer's method. X equal to 1, y is equal to 2, z is equal to 1. Now let's proceed to Gaussian elimination method. So for Gaussian elimination method, the elimination process of solving a linear system starts with the augmented matrix of the system. So that's the first step, okay, when we use Gaussian elimination. So we have to um, create the augmented matrix of the system of linear equations. So the process continues until it has led to a matrix in which zero element or in which every element below or above the diagonal elements is zero. Okay, so such a matrix is said to be Gaussian, and the process whereby elementary row operations are used to reduce a matrix to Gaussian form is called Gaussian elimination. As soon as the augmented matrix of a consistent linear system has been reduced to a Gaussian matrix, the system corresponding to the Gaussian matrix can be solved by back substitution. Okay, so actually the Gaussian matrix, okay, that is mentioned here, that is actually uh, an that is actually a triangular matrix. Now, since it is mentioned here that that Gaussian matrix, the elements below or above are zero. Above the diagonal elements or the principal diagonal are zero. So meaning to say that matrix is an upper or lower triangular matrix, right? So these are the steps in Gaussian elimination method. So the first step is we have to write the system of linear equations to augmented form. Okay, the second step, we have to let the leading element or the first element of the augmented matrix be B1, okay, by interchanging two rows or normalizing the first row. So the leading element cannot be 0. So the element located in the first row and first column, we should make it 1. Okay, so it should be 1, and it cannot be 0, ha? Okay, so we will make that leading element as 1, okay, by interchanging two rows. So interchanging two rows means to say, if there are rows, okay, wherein the first element of that row is 1, we can interchange that to the original first row, okay? So that the leading element of that augmented matrix will be 1. Or if there are no rows that have 1 as the leading element or the first element, okay? So we can also normalize the first row. So normalizing the first row, we just have to multiply a scalar quantity to the first row in such a way that the leading element will become 1. Okay, so we will see that in our example. No? Now, for the third step, we have to reduce the augmented matrix to upper triangular matrix, also called row echelon form by elimination. Okay, so we can do that, okay, that the augmented matrix can be reduced to upper triangular matrix, okay, by multiplying any row by a non-zero scalar. So in this case, no, we can multiply the normalized first row. No, so we can multiply it by the coefficient, okay, of the other rows, okay, and then after that we will subtract or add that row that we multiply with non-zero scalar, okay, so that it can be cancelled. Okay, so from that, no, if we already reduce that augmented matrix to upper triangular matrix, we can now solved by back substitution. No? So here, it's important to notice here in step 3. No? So for this course, no, we are going to reduce the augmented matrix to upper triangular matrix. No? Just for us to be uniform in solving using Gaussian elimination. So instead of using lower triangular matrix or any of those two, okay, we will use upper triangular matrix. Okay, we will reduce the augmented matrix to upper triangular matrix. So this will now be the steps, okay, in Gaussian elimination. So we can now start solving using this method. So solve the system of linear equations using Gaussian elimination method. So we have here a system of linear equations, 3x plus 2y plus z is equal to 8, 2x plus y plus 3z is equal to 7, 5x minus 3y plus 4z is equal to 3. So using Gaussian elimination for our solution, so we have to find for the values of x, y, and z, okay, to solve this linear or to solve this system of linear equations. And for our solution, our step 1, we have to write the system of linear equations to augmented form. So we will rewrite this system of linear equations to augmented form. So the augmented form, we just have to write here the coefficient matrix, and beside this coefficient matrix are the constants. So the constants are 8, 7, and 3. So now for our second step, okay, we have to let the leading element or the first number or the first element of the augmented matrix be 1 by interchanging two rows or normalizing the first row. Okay, so again, the leading element cannot be 0. So here, our leading element here is this element. Okay, so we should make the leading element as 1. Okay, so we have two choices here. We can interchange rows. Okay, if there are row here that wherein the first element is 1, okay, we can interchange that to the first row. No, but since there are no rows here wherein the first element is 1, so we will not use interchanging rows. Okay, so instead we are going to use normalizing, no? So we are going to normalize, okay, the first row. So we will normalize the first row, okay, by multiplying this row, okay, in with a constant or a scalar quantity wherein this 3 will become 1. Okay, so in order for this 3 to become 1, we will multiply this by 1/3. So this will be 1/3 R1. Okay, so this 1/3 R1, it will become the new first row, okay, of this augmented matrix. Okay, so we will multiply all the elements of the first row by 1/3, no? And that will be the new first row for the new augmented matrix. So it will be 1/3 times 3, so that will be 1, and then 1/3 times 2, that will be 2/3. That 1/3 times 1, that will be 1/3. 1/3 times 8, that will be 8/3. So this will become the new first row, okay, of this augmented matrix. And the remaining rows, it will just be the same. Okay, so for our step 3, we have to reduce the augmented matrix to upper triangular matrix, okay, by elimination. So we have our goal here, okay, is to make this augmented matrix. Okay, we have to reduce this as an upper triangular matrix, no? So this will be the upper triangle form, no? So these values, these 2, 5, and -3, okay, elements, they should become 0. Okay, in order to do that, okay, we are going to multiply, okay, our first row. We are going to multiply our first row to this coefficient, no? So this is 2, okay, and we are going to subtract that the row 1 multiplied by 2. We will subtract R2 so that we can cancel this 2, no? So that it will become 0. So that is our goal, to make this 2 0. And also we will multiply our first row by 5 since the coefficient here is 5. So we will multiply our first row by 5 and subtract R3 so that 5 will become 0 to our new to the new third row, no, in the new augmented matrix. So we will perform this. So 2R1 minus R2, that will become the new second row, and 5R1 minus R3, that will be the new third row. Okay, so performing this. Okay, so 2R1, so that will be 2 times 1, okay, minus R2, so minus 2, okay, that will be 0. And then we have here 2 times 2/3 minus 1, okay, so that will be 1/3. Okay, so we can use calculator here, no? So again, for 2 times 1/3, okay, so that will be 2 times 1/3 minus 3, so that will be negative 7/3. So that will be negative 7/3 here. Now, 2 times 8/3, okay, 2 times 8/3 minus 7. Okay, so this will be negative 5/3. So it will become negative 5/3 here. Now, for this equation, so 5 times R1, so that will be 5 times 1 minus R3, which is 5. So that will be 5 times 1 minus 5. So that will be 0. Okay, and then 5 times 2/3, 5 times 2/3 minus negative 3. So that will be 19/3. Okay, and then we have here 5 times 1/3 minus 4. So that will be negative 7/3. And then we have here 5 times 8/3 minus 3. Oh, so that will be 31/3. So that will now become the new second row and new third row. Okay. So from the new augmented matrix here, so as we can see here, these are already 0. So our goal is this 19/3, okay, it should also become 0. So we can do that, okay, by normalizing first, okay, our second row. So we have to normalize our second row. Okay, normalizing it meaning to say, okay, so this 1/3, it should become 1. Okay, so we have to multiply this row, okay, the second row, by a number in such a way that this 1/3 will become 1. So we will multiply the second row by 3. Okay, so we will multiply the entire second row by 3, and that will become the new second row of the new augmented matrix. Okay, so this will become 3 times 1/3. Actually 3 times 0, so that will be 0. And then 3 times 1/3, that will be 1. 3 times negative 7/3, so that will be negative 7. Okay, and then 3 times negative 5/3, that will be negative 5. So this will now become the new second row. So from this, no, so we can now multiply our second row by the coefficient that we want to cancel, which is 9/3, no, and we just have to multiply the entire second row by 19/3 and subtract the third column to make this 19/3 0. So 19/3 R2 minus R3. Okay, so that will become the new third row. Okay, so performing this, okay, so this will just be 19/3 times R2. So this is the second row minus R3. So this is the third row. So this will be 19/3 times 1. Okay, minus 19/3. So that will be 0. And then 19/3 times negative 7, okay, minus negative 7/3. So if you input that in your calculator, again, 19/3 times negative 7 minus negative 7/3. So that will be negative 42, right? And then we have here 19/3 times negative 5 minus 31/3. So that will give you negative 42. Okay, so from here, this is already an upper triangular matrix. Okay, so we can now start performing the fourth step, which is solving by back substitution. So solving for back substitution, meaning to say, we will use this, and this is negative 42, and this column is actually the column for z variable, no? So this will become negative 42z, okay, is equal to negative 42. And solving for z, so this will be equal to 1. Negative 42 over negative 42, that will be equal to 1. So this will now be the answer for z. Okay, now for y, so we will use this, no, the second row. So this will be 1y my plus negative 7z is equal to negative 5. Since we already have the value of z, which is 1, so we just substitute that. So our y will become negative 5 plus 7. So that will be 2. So our y is 2. So that will be the value of y. Now for x, that will just be 1x plus 2/3 y plus 1/3 z is equal to 8/3. Okay, so we already have the value of y and z. We just substitute that. Okay, so this will now become x times 2/3. Okay, times 2 plus 1/3 times 2 is equal to 8/3. So solving for x, that will just be 8/3 minus 2/3 times 2 minus 1/3 times 1. So that will be equal to 1. So this will now be the values of x, y, and z. This will now be the answers for this problem using Gaussian elimination. So let's proceed now to Gauss-Jordan elimination method. So this method is actually similar to Gaussian elimination method. So there are just some steps that are altered in the Gaussian elimination, no, for this method. Okay, so here are the steps, okay, for Gauss-Jordan elimination method. So the first step, okay, is you have to write the system of linear equations to augmented form, which is the same first step in Gaussian elimination, right? And our second step here, we have to let the leading element or the first number or first element of the augmented matrix be 1 by interchanging two rows or normalizing the first row. So the leading element cannot be 0. So this is also the same second step in the Gaussian elimination. So the third step, we have to reduce the augmented matrix to unit matrix, also called the reduced row echelon form by elimination. So this is the step that is different from Gaussian elimination. If in Gaussian elimination, we have to reduce the augmented matrix to upper triangular matrix. So for Gauss-Jordan, we have to reduce the augmented matrix to unit matrix. So unit matrix, this is a matrix wherein the principal diagonal are all 1. Okay, and the remaining elements, okay, are all zeros. Okay, so that is a unit matrix, and that unit matrix, it is also called reduced row echelon form. So we're going to do that. Okay, we're going to reduce that augmented matrix to unit matrix by elimination. So just like what we are doing in Gauss-Jordan elimination, we multiply the row that we normalize, okay, by the coefficient, okay, of the rows that we want to cancel, no, to cancel that element, no. And we are going to just analyze if we're going to subtract or add those rows, no. And so let's start solving using Gauss-Jordan elimination. So let's solve the system of linear equations using Gauss-Jordan elimination method. So this is actually the same example that we solve using Gaussian elimination method. No? So supposedly, the answers for this, okay, should be the same, okay, if we solve this using Gauss-Jordan elimination. So again, to solve for this system of linear equations, we just have to solve for the value of x, y, and z. Okay, so for our solution, our step 1, so this is the augmented matrix, okay, of this system of linear equations. Now, for our second step, we just have to make the leading element 1 by interchanging. So again, there are no rows wherein the first element are 1, so we cannot do interchanging two rows. No? So instead, we are going to normalize the first row by multiplying the first row by 1/3 to make this 3 1. So normalizing it, okay, so multiplying the entire first row by 1/3, so it will give you 1, 2/3, 1/3, and 8/3. So from here, we can now proceed to our step 3. So we have to reduce this augmented matrix to unit matrix. So meaning to say this matrix, no, it should be, its principal diagonal should be 1 and the remaining element should be 0. No, so that's the unit matrix. So that's our goal, okay, for this augmented matrix. We have to reduce this to a unit matrix. So we are going to do what we are doing in Gaussian elimination as well. So for this, no, so to make 2 and 5 0, we are going to multiply R1, okay, by 2, and then subtract that 2R1 2 or by 2, row 2. Okay, so that will be 2R1 minus row 2, and that will become our new row 2. Now, we are going to multiply also our first row by 5, okay, and then subtract the third row, okay, so that this 5 will become 0 to our new third row. Okay, so again, we are going to perform this. So performing this, so 2R1, so 2 times 1 minus R2, so R2 is 2. So 2 times 1 minus 2, so that will be 0. So this will be the new row 2, ha? Okay, and then proceeding now, 2 times 2/3, okay, minus, okay, 1. Okay, so that will give you 1/3. So input that in your calculator. Okay, then we have here 2 times 1/3 minus 3. So that will give you negative 7/3. And we have here 2 times 8/3 minus 7. So that will give you negative 5/3. So this will now become the new second row. Now for the new third row, we're going to perform this. So this is 5 times R1. So 5 times 1 minus R3, which is 5. So 5 times 1 minus 5, that will be 0. And then we have here 5 times 2/3 minus negative 3, so that will give you 19/3. And then 5 times 1/3, okay, minus 4, that will give you negative 7/3. And then 5 times 8/3 minus 3. So this will now be the new augmented matrix. So this will be the new second row obtained from the operation that we performed in the previous slide. No? So this will be the new second row. Okay, now, since the second row is now normalized, no, so we can use this, no, to make this 2/3 and 19/3 0, no, so that's our goal, to make them 0. Okay, so by multiplying the second row, okay, to 2/3 and 19/3, and then we are going to analyze if we're going to add that row to that another row or subtract it, no. So for the second row, okay, if we multiply this by 2/3 and subtract 2/3 R2 minus R1, so we cannot do that because this new row, new first row, it will become negative 1 since 2/3 R1 or R2, 2/3 R2 minus R1. So meaning to say it will become 0 minus 1, right? So we cannot do that. So instead of 2/3 R2 minus R1, so we will make it R1 minus 2/3 R2 instead. Okay, and that will become our new row 1. Okay, so we are going to use this. Now for this one, no, to cancel this, so we have to multiply our second row by 19/3. Okay, so that will be 19/3 R2, and then we just have to subtract R3, no? So that will become our new row 3. Okay, so performing this, operations, okay, so for R1, so R1 is 2/3 minus 2/3 of R2, which is 1. So 2/3 minus 2/3 of 1, that will be 0. So that will be 0 here. Okay, and then we have here R1, that is 1/3 minus 2/3 of negative 7. So that will be 5. Okay, and then we have here 8/3 minus 2/3 of negative 5. So that will be 6. Okay, so this will now become our new first row. Now for the new third row, so we will perform this. So this will be 19 thirds times R2. So that will be 19 thirds times 1 minus R3, which is 19 thirds. So 19 thirds times 1 minus 19 thirds, that will become 0. And then 19 thirds times negative 7 minus negative 7 over 3. So that will be negative 42, right? And then we have here 19 thirds times negative 5 minus 31 over 3. So that will give you negative 42. So from here, this is not yet a unit matrix. So in order to make this a unit matrix, we have to normalize this third row. No, we have to make this negative 42 as 1. Okay, so normalizing it. Okay, so we have to think of a number that we can multiply to the third row in order that this negative 42 will become 1. So we are going to multiply the third row by negative 1 over 42. Okay, in order that this negative 42 will become 1. So multiplying the entire row of row 3 by negative 1 over 42, it will give you negative 100, negative 1 over 42 times negative 42, that will be 1. Negative 1 over 42 times negative 42, that will also be equal to 1. Okay, so this will now become the new third row. Okay, so again, this is not yet a unit matrix, so we have to make this 5 and negative 7 0. So we just have to multiply this third row by these elements, no? So to cancel these elements, and we're going to multiply or add this row to that to another row, no? So okay, so let's perform this, no? So for the third row, we are going to multiply this by 5. Okay, again, we cannot do that. We multiply the third row by 5 and then subtract by R1. Again, we cannot do that because it will become 0 minus 1. So um, the new first row, okay, it will become positive, it will become negative 1, no? So that cannot happen, no? So instead of that, no, so we're going to use R1 minus 5 R3 instead. Okay, so that R1 minus 0, which is R3, no, 0, so that will be still positive 1, no? Okay, so that will become our first row. So this is this is first row. Okay, so now for the second row naman, so we're going to multiply our third row. We're going to multiply our third row by 7. So we can multiply our third row by just 7 since this is negative 7, and then just add the second row to cancel negative 7. And this will become our new second row. Okay, so from here, we are going to perform this. Okay, so for performing this, so R1, so our R1 is 1 minus 5 R3. So our R3 is actually 0, no? So this will be 1 here. So let's proceed directly here. So this is R1. So R1, that will be 5 minus 5 R3, which is 1, no? Negative 5 times 1. So that will be 5 minus 5. So that will be 0 here. And then we have here 6 minus 5 times 1. Okay, so that will be 1. Okay, now that will become the new first row. Now for the new second row, so 7 times R3. So 7 times R3, that will be 7 plus negative 7, right? So that will be 0. So it will be 0 here. And then 7 times 1 plus negative 5, so that will be positive 2 here. So this will now be the new second row. Okay, so from here, so this is already an identity matrix. So from here, actually, the answers for x, y, and z will be the new constants here. So this will now be the value of x. X is equal to 1, y is equal to 2, and then z is equal to 1. So this is the value of x, this is the value of y, and this is the value of z. So this will now be the answer for this problem using Gauss-Jordan elimination method. Okay, so x equal to 1, y is equal to 2, z is equal to 1. Let's proceed now to matrix inverse method. So the steps for this method, the first one is we have to write the given system of linear equations as a single matrix equation. So we just have to rewrite this, no, this system of linear equations into its matrix equation or matrix form. No? And the second step, we have to solve the matrix equation obtained in step 1. No? So we have to find the x. No? So here in this matrix equation, so we can actually denote this coefficient matrix as capital letter A. And then we can denote this column wherein this is a column of all the variables x, y, and z. So we will denote this as capital letter X. And then we will denote all the constants B1, B2, B3 as B. Okay, so this A times X equal to B, this is actually this matrix equation, no? So this A times X equal to B. Okay, so if we multiply both sides of these equations by the inverse matrix, okay, of matrix A, okay, or inverse of matrix A, so we multiply both sides by inverse of matrix A, so A raised to negative 1, A raised to negative 1. And since we know that A raised to negative 1 times A, okay, so if you can remember, okay, in our second method in solving for the inverse matrix, right? So we know that A times matrix A times the inverse matrix equal to I. So this A raised to negative 1 times A, this is actually equal to I, or the identity matrix, times X is equal to A raised to negative 1 times B. And here, we will realize when we solve that if we multiply identity matrix to X, okay, or to this column X, Y, Z, no? So it will just be, it will remain the same. It will remain as X, Y, and Z. Okay, so meaning to say, our X here will just be equal to the inverse matrix A times B. So this will just be X, Y, Z is equal to the inverse of this matrix A times a constants B1, B2, and B3. So we will use this formula. Okay, so solve the system of linear equations using matrix inverse method. So to solve this, no, we just have to solve for x, y, and z. Okay, so using matrix inverse method, so our first step, we have to write this system into its equivalent single matrix equation. No, so this is the matrix equation, okay, of this system of linear equation. So for the coefficient matrix, so that will just be 1, negative 1, 3, and then 2, 1, 2, and then negative 2, negative 2, 1. Okay, so that will be the coefficient matrix. And this column matrix, no, this will just be the unknown variables x, y, and z. Okay, and we will equate this to the constants 2, 2, 3. Okay, so after the step 1, we will now proceed to the second step. So solve the matrix equation obtained in step 1. No? So we have to find the x, or the column of variable x, y, and z. So we're going to use this formula. No? So we have to solve for the inverse of matrix A. So the inverse of the coefficient matrix A, no, if you're going to solve that using the methods that we have discussed, okay, in solving for the inverse matrix of A, inverse of matrices, no? So the inverse of matrix A will be this matrix, no? So I will not show you here how to solve for the inverse matrix of A. So you can solve that on your own using the methods that we have discussed, okay, in course material number 3, no? So try solving it on your own. So this will be the inverse matrix, okay, of matrix of the coefficient matrix A. So we're going to use this in our formula. So in our formula, this is So I will show you here, no, that if we multiply the identity matrix to X, it will just remain as X. Okay, it will just be the same, no? But I will show you here. So the identity matrix here will be a 3 by 3 since our matrix here is 3 by 3 as well. Okay, so this will be 1, 1, 0, 0, 0, 0, 0, no? So this is our identity matrix multiplied by X. This is the column of the variables X, Y, and Z, and we will equate this to the inverse matrix that we have here. So again, I will not show you how to solve this, no? So you can solve it on your own using the methods that we have discussed in CM number 3. So this is the inverse matrix of coefficient matrix A. Okay, and we will multiply that by B, or the constants 2, 2, 3. Okay, so if we multiply this identity matrix to X, Y, Z, this will just be 1 times X plus 0 times Y plus 0 times Z. So it will just be X, right? And then 0 times X plus 1 times Y plus 0 times z, so that will just also be y. And for this, 0 times x plus 0 times y plus 1 times z, it will just be z. So it will just be x, y, z. And then here, we are going to perform this, the operation for this. We're going to multiply this 3 by 3 matrix to this column matrix. No? So this will just be 1 times 2, okay, plus negative 1 times 2 plus negative 1 times 3. Okay, so inputting that in your calculator, it will give you negative 3. Okay, then we have here negative 6 over 5 times 2 plus 7 over 5 times 2 plus 4 over 5 times 3, and it will give you 14 over 5. And then negative 2 over 5 times 2 plus 4 over 5 times 2 plus 3 over 5 times 3, it will give you 13 over 5. So this will actually be now the values of x, y, and z. So applying the concept for equality, so x will be equal to negative 3, y is equal to 14 over 5, and z is equal to 13 over 5. So these will now be the answers for this problem. So that concludes our discussion. I hope that you learn, and I hope that you attain the learning outcomes for this topic. Reminder that there will be CM assessment task for this topic. Okay, you have to answer that, and you have to submit that on our next meeting. So happy studying, class. Keep safe and God bless. Bye-bye.